welcome back. We will look at ADC errors and we will try to get a comprehensive view of this aspect of ADC, because in IoT we will be sensing, right. So, the sensor is connected to an ADC port, and if you do not understand the functioning of the ADC and errors associated with ADC, your values that you get for any sensing application and sensing and control application can be disastrous. So, particularly industrial IoT or medical IoT, sensing value should be perfect, right. If you are building a ventilator and you are looking at the exact pressure value of which you are sensing, it should be perfect. Okay. So, that you cannot blame, you cannot say that I bought the best sensor but I did not get a good performance from the electronic system. It is because of your limitation to understand how the ADC works, how it actually converts. Now, as IoT engineers, what are the things, what are the sources of this error, you have to understand. Okay. This is a very so this is very clear, and in fact this error and error budgeting and working with errors is a reality. Okay. There is nothing like ideal anywhere. If you take a picture like this, okay, let us, I will just give you a, I mean this is something that I was seeing somewhere, and then I thought this will be nice to introduce even here. Okay. Let us say this is the true value of something, this is the true value, this is the actual value, okay, of the sensed output, this is actual value. But when you actually did all the sensor, you took the sensor, connected to the ADC, and you connected and you looked at the output, your value was here. So, this is the measured. So, actual is this, measured means when I say I have also included the error in the measurement already. Measuring equipment also can have an error, right. Plus you connect it to ADC, it will also give you a certain error. So, we will factor all of them slowly. This is your measurement value, or by a measurement you got this value. So, this is actual measurement value. Okay. Then when you did, so first time when you measured you got this value, you got this value, but then when you did another measurement, this line perhaps shifted to this point. Another time when you did a measurement, this line perhaps shifted here. Okay. Another time when you did a measurement, it perhaps went here, and when you did another measurement, it went here. So, you can go on doing these measurements, okay, and you can arrive at, so let me put it back. You did all these measurements repeatedly, and what you got is not a single line here, but you got a distribution of errors. Okay. In other words, you could see that this is now become the mean, it is like a mean, and there is a distribution of errors here. So, and this is usually Gaussian and so on. So, this is what you got. Now, you can say this is the error which I can easily correct. I can correct this, because if I know this line, I know my actual line, I know this line, I can more or less correct it for it, so that I can add some value, some offset, some bias, something I can do, and I can correct this this measurement value that I got here. This is this kind of fixed line or fixed distance between the actual and the measurement, which you can correct, because you are able to measure and you can quantify it and correct it, clearly indicates this is called systematic error. Systematic. Okay. Systematic errors can be corrected. What you have difficulty is this part here, okay, all these regions you do not know where exactly that value comes because this is random. Therefore, this is random error. Okay. This is random error. So, any ADC will have systematic error and will have random error, and you can only look at data sheets and understand all the error values which are mentioned in the ADC and understand them carefully. You may not want to sort of worry about it because any ADC is, there is no ideal ADC, okay, there is no ideal ADC at all, bound to have lot of errors. You should know how to work with them, work with those errors. So, this is a sort of a, I would say this picture on the right side is more of a general understanding. We will try and see how to map it into the ADC, but in general any error you should first be clear that you can those errors which are correctable, which you can measure and sort of apply a certain offsets and you can correct them, which are essentially systematic errors, and then there are random errors. Random errors are difficult to catch. Okay. Now, let us come back to this picture on the left side. So, I will draw a line here and we will just worry about this line. See, if you apply a certain input voltage to an ADC, this is your ADC, okay, this is what you are applying here is analog input, what you are getting is a digital output. What I did here was I plotted the input versus the digital output. This is also called often they call it by a name called transfer function. Transfer function. You can look up, there are a lot of material related to transfer function, but I will try and give you a very intuitive understanding because you need that as a basics for all your design for your design and choice of components and so on. So, you need to look at those data sheet parameters. If you take an ideal ADC, any small input that you apply here, you will have a corresponding digital output, right. Any small variation, any small input you will have. So, in a way this line will become continuous. You apply a voltage here, you will get one point here. You apply a very small voltage here next to that, infinitely small increment over the existing voltage, you will get one digital output. That kind of ADC is very ideal, it does not exist at all, and it does not exist because of what we discussed previously. Look at this picture. So, what actually happens is when the input is coming here, right here, AC input, okay. So, let me remove this and show n like this, much higher frequency comes and so on. So, this frequency input high input signal is coming here, this capacitor has to charge, and I mentioned to you that the output has to hold when the capacitor is read, so that you get the digital output. Now, this has a certain latency associated with the operation, right. All this actually means that there is something called a conversion time. There is a conversion time, and then there is also so closely associated with the conversion time is the sampling rate, okay. So, you can sample it only at a finite rate, and that depends on the sample and hold circuit, the impedance offered by the ADC and so on. So, so many parameters are associated with it. Anyway, abstracting all that simply means if there is a finite time over which the ADC takes to convert the input to the output, and there is the sampling rate, the minimum and maximum sampling rate that the ADC supports, very high frequency signals input voltages will keep changing, right. So, at very high rate that signal is now lost, that next level of voltage is actually lost. There is no way by which you can convert that small voltages which are arriving. Therefore, what it boils down to is that you cannot have an ideal ADC line like this, it is not going to work at all. So, what you will have is some input voltage up to one point, any voltage up to this point will have a corresponding digital output. This will be the code word output. So, then what happens, up to the next point it will remain the same code word. Any voltage here is still represented here only, right, it is still represented by this point only, and once it touches this point, the input voltage comes here, you will get a corresponding code word output, and then it goes on like this. So, the next point is here and so on. Now, so up to from this point to this point, it is all represented by this value only, and from here onwards whatever is increased in voltage will still be represented like this and then like this. So, think about a staircase, you are climbing a staircase and you are moving all the time on the staircase, right. So, the point is this is ideal, and this is also an is also a perfect, this is also a perfect ADC in a way, not ideal but perfect, it is doing what it is supposed to do. Okay. Now, the point is you do not have perfect ADCs also, that is the problem. That is why I have shown this right side picture. If you had a perfect ADC, you would have no issues at all, everything is sane in a way. Also, let us consider an example of to understand the transfer function by taking a reference voltage of 1 volt. Alright, if you take 1 volt as the Vref, the first code word generates for Vref of 1 volt into 2 power n, and you want to know the first code word. So, this will be 0.125, it will be 0.125. If you have 0.125 volts, you will get the first code word, you can check this. The second code word will come when it is anywhere between 0.125 into 2 divided by 1 volt into 2 power n, which is again cubed in our case, you will get the second code word. So, now if you now map this into this picture, let us put it here, any voltage from 0 volts to 125 millivolt will simply read all zeros, the very first code word which is 0. Then the second one is the from 125 to 125 into 2, which is 250 millivolts. This up to 250, from 125 to 250 millivolt, it will read the second code word, and that second code word corresponds to digital output of 001. Okay. So, this is how it should work, this is how it should work. Take a voltage source, power supply for instance is a voltage source, a simple power supply, put it to 0 knob, put it to complete, shift the knob to complete 0 volts. There are two knobs, you can do current limit adjustment and voltage adjustments, right. So, this is your voltage knob. If you change this knob to the right, the voltage increases, there is a small meter which will tell you, right. There is a meter here, this meter with graduation will show you increase in the voltage, slowly it will keep changing. Now, supposing you start from 0 and you start slowly moving this knob to the right, you will find to your surprise that the first digital output for the 0 volts, you leave that aside, the first code word output which is 001, right, that actually occurs not at 125 millivolts, but it occurs much early. In fact, if you move the knob to 62.5 millivolts or thereabout, I am being very careful, 62.5 millivolt or thereabout, okay. You may already see 001, that is the point. I use the word thereabout because I am not sure, you are also not sure for that ADC whether it will trigger at half of 125 millivolt, which is 62.5, or whether it will trigger to the second code word at 50 millivolt, or whether it will trigger at 80 millivolt. We do not know this, we do not know this for sure, but for sure it will never trigger at 125 millivolt, it might trigger much earlier. It is also possible it may trigger even later. Why should it trigger at 125 millivolt? It may also trigger at 130 millivolt, it may trigger even at 140 millivolt. You really do not know till you actually make a measurement. So, you need a multimeter, you need a digital output, and you should be able to read those values, which essentially means it is not an ideal perfect ADC at all. Now, how do you account for all this? But one thing you can tell for sure, if it triggers at, let us say, at 62.5 millivolt, the next trigger will definitely be after 125 millivolts, that you can be sure, okay. To some extent you can say that that additional point will come after periodically after every 125 millivolt. Now, go back to this picture, to the right side picture. This clearly is a systematic error, right. You have a systematic error. That systematic error can be easily corrected, Therefore, it is easy for you to modify this expression, which is code word is equal to V in divided by V ref into 2 power n, can easily be modified as V in minus V offset divided by V ref into 2 power n. This can be easily said, you are subtracting that, okay. This is something that you can already factor in for input offset error, one of the first systematic errors. Similarly, I will give you a feel for one more type of error that crops in, okay. And that is, so now we discussed about this side, you took a multimeter from 0. There is another problem as you move on towards the maximum voltage. The maximum voltage, as you are moving up the ladder, we took this as 1 volt, as I mentioned to you, right. You will actually get the final code word, which is corresponding to digital value 111 much early. That also is another issue for you. In other words, this infinite resolution 45-degree curve can actually go a little more steeper, okay, and it might reach to a voltage which is much before the actual voltage that should have triggered the output voltage, okay. This is called gain error. This is another problem. Again, this gain error can be factored into the code word. because it is also a systematic error. So, people use a convention of modifying. So, this is your expression 1, this is your expression 2, and the third expression is including the gain error. So, let me put expression 3, which is code word is equal to V in minus V offset V ref into 1 minus gain times 2 power n, but I will tell you that the gain terms comes here. So, this is the final expression, and the code word itself that you are getting, which is nothing but corresponding to the digital value. The digital value as seen in this transfer function this is digital value. Okay. As seen from this transfer function is clearly triggering at the lower side, relates to offset error, and the issue of arriving at the final code word ahead of the actual voltage is indeed the gain error. These are the two things which are systematic by nature. So, this is the final expression which included the offset error as well as the gain error. Now, there are some formal definitions which you have to note. Okay. So, for example, the definition of gain error is typical of what people say is the error associated with a data converter, which is full scale error minus the offset error, full scale error minus the offset error. Okay. This is the gain error. So, gain errors are typically defined as full scale error minus the offset error. Full scale error, what is full scale error? Full scale error, how do you do that? Is measured as the last ADC transition ADC transition on the transfer function curve and compared, this is important, and compared against the ideal ADC transfer function. So, this is important. Okay. So, gain error is defined as the full scale error minus the offset error, and the full scale error itself, how do you measure it? Last ADC transition on the transfer function curve and compared against the ideal ADC transfer function. So, these are important points that you will have to look up in the data sheet. Data sheets will talk about the offset errors and the gain errors. Now, that is, these two parameters are insufficient for you. You need to also look up the other type of error, and I will show you what the other errors are. Normally if you consider the this picture, we wrote here some numbers 0, 125 millivolt and so on, right, which is essentially our example of taking FSR as 1 volt and 3 bit resolution, then we get this 125. This is from 0 to 125, we said the transition is from 000 to 001, that is the next code word. Usually they do not express, the community does not express in terms of voltages, they usually express in terms of LSBs. So people talk about how many LSBs, because if the reference changes, if your FSR voltage changes, if your Vref changes, this voltage has no meaning, right. It will, if it is 5 volt, it is something else, if it is 1 volt, it is 125 as we saw. Therefore when people talk about the steps and talking about errors, people talk in terms of LSB errors, okay, the number of LSBs associated with it. Therefore you can see that an ideal ADC you can never have, because you need infinite resolution, and this is a resolution which we have seen, which is like a step. Errors associated with ADC, people refer to them as plus minus of LSB or plus minus of half LSB. It is easy to connect, you do not want to refer in terms of voltages, but you want to refer it in terms of LSBs. So that is the usual convention. So now let us go back to the data sheet. Now it is easy, as you can see that this data sheet can be understood better in the following way. The ADC has the ADC of interest is a 12 bit resolution. It has plus minus 1 LSB of DNL. DNL stands for differential nonlinearity, and integral nonlinearity is also plus minus 1 LSB. Then other parameters associated with it are also mentioned to you. As we go along, you will see in this data sheet that several things would be clearer as we move on. So let us see the other data sheet parameters. Right, you can see here the offset error, look at just this DC accuracy. Integral nonlinearity error is expressed in typical, there is a typical value and there is a maximum value of plus minus 1 LSB. Differential nonlinearity error is plus minus 0.5 typical and a maximum of plus minus 1 LSB, right. No missing codes over temperature. What is this, right? So you have to be careful about understanding what this actually means. That means there are some missing codes. Yeah, the answer is yes, actually there are some missing codes, and we will come to that missing codes. Anyway, before we move on, offset error plus minus 3 LSB maximum, typical is plus minus 1.25 of an LSB, and then gain error is plus minus of 1.25 and a maximum of plus 5 LSB. Great. Before we understand, our immediate attention goes to what is this missing codes. So I will show you what this missing code problem is when we come to the differential non-linearity. In the case of ADC, this is your ideal, right, and you would essentially have, this is your transfer function which we know it so well now. This is your V in or input voltage, and this is your digital output. Let's simply say output, and this is, so I will just move this arrow so that we will be able to accommodate 001, and I will also move this now that we know it is, and so on, right. See, what actually happens is the ADC's performance, what should happen? Ideal, let us go back to the ideal case. Till here it will be all zeros, and then it will transit to, let us move this a little bit so that we can map it to 0 0 1 here, and then it will remain, then come up again here and then up here. This is what we know very well now, right, and so on. If an ADC is not performing up to the mark, at this point what would happen is, okay, it should have triggered here, this line will be missing. So, what it will trigger is this, instead of triggering the previous code 0 1 0 0 1 0, then it should be 1 0 0 and 1 1 0. This code is gone, it will never give you that. This is your, it will miss completely. What actually happened was the input voltage changed in a normal way, but ADC is so non-linear that it skipped one digital output. So, skipping of digital output is also possible. That need not happen here, it can happen here. For some ADC it can happen here, some ADC it can happen here. So, it is all random, okay. Input would have changed, but code output would not have come, it would have skipped that and gone to the other one. This problem also occurs, and this is nothing but the differential nonlinearity. Similarly, integral nonlinearity. Integral is nothing but accumulation of the differential nonlinearity itself. Again, it is good to understand this pictorially. So, let us do that pictorially. So, if you remove all this and look at the transfer function curve, some places it may go low, some places it may go high, it may go like this. This is integral nonlinearity. This is your I, which you saw it here, integral nonlinearity. It's nothing but accumulation. So, now you should know how to design with gain error, with offset error, with known DNL, and integral nonlinearity. I would like to leave it at this stage, because this is a basic course on ADCs, we should not delve into too many details, but at the same time this is important to know. There is one more important parameter which you must know, okay, which actually relates to the accuracy of the ADC, and that point I would like to discuss with respect to an important picture here, which is referred to the VREF. See, this VREF also you have to put a lot of attention, pay a lot of attention to VREF, because the VREF is the one that is being used for the comparator operation. If the VREF changes, the output will change. Now you have compounded the problem by the code output that you are getting, the digital value you are getting is not because of any non-linearities which you have anyway you have to battle, the errors associated with the actual component, but you have to battle the voltage that you have applied to that. Okay. Why is that important? It is important because when an ADC is powered in an IoT device, an IoT device SoC has a power supply section which may contain a linear regulator or it can contain a DC-DC regulator. Now the ADC is receiving power from one of them, either this or from this one of them. Now if it is receiving power from DC-DC, there is a lot of switching noise which is associated with DC-DC systems. If it is LDO, linear dropout, then it is a lot more smoother. Now if VREF is applied internally to this ADC, and if VREF is fluctuating randomly, then the output, ADC output also will change. This is one problem. So you have to be careful on how are you powering the internal ADC. Is it through linear power supply or is it through a switching power supply? This is one part. Second part is also about the fact that if VREF is noisy, because this essentially means if VREF is noisy, output will be unpredictable again. So you need a VREF which is stable. Okay. Usually if you take Arduino and other controller boards that you know very well, okay, pay a lot of attention, so I will put one mark here, pay attention to VREF. You can configure internal, you can configure external, or you can configure it from coming directly from VCC. Any of these three things are possible. Arduino code has specific settings for you to choose so that you can keep the VREF as stable as possible. For any accurate measurement, it is good to use very accurate stable voltages which you can feed into an ADC from outside, that is called external VREF. If you are choosing from within the chip, choose internal, but choose something which is also very stable, which will give you a very stable reference. Inside the chip they usually use what is known as a band gap reference. So you try to choose the band gap reference as much as possible. The only issue with band gap of our internal references are, in fact even that is true for Arduino internal reference, I think the internal reference of Arduino is a little over 1 point some voltage, I think it is 1.1 or 1.2 volts, I do not recall correctly. So it is a little over 1 volt. So in other words, any comparisons that you are doing is typical of the sensor output giving you anywhere between 0 and 1 volt, keeping your reference at 1 volt. So you have to think about what is your sensor, what is your sensing parameter, and what is it that is giving from its lowest value to the highest value, and based on that range you have to choose the VREF, very important. Supposing it is giving you 2.2 volts at the maximum, and let us say it is giving you 100 millivolts or 0.1 volts at the minimum, you can't choose a reference which is at 1.1, it is not going to work because it is going to saturate. Therefore choice of VREF is a very important design parameter, okay. That is number one. Number 2 is it is always good to choose this Vref as high as possible. Okay, on the other side you can say that it is good to choose a high Vref as well, maybe 3.3 or even 5 volts, because if you choose a higher Vref, the SNR, signal to noise ratio, of the ADC also improves. Its ability to cut off noise is also good at higher references. So, Vref is an important parameter. As we go along, I will give you some material to read from on Arduino and so on, which will allow you to understand this issue of noise in ADC, Vref in ADC as critical parameters for several of your sensing applications. Now let us complete this discussion on sensor interfacing to a IoT device, an embedded device. Let us draw our attention to a important sensor which is basically measuring nitrogen dioxide, and that sensor essentially is a semiconductor sensor. It is also measuring carbon monoxide, both, it is giving you both. And one such sensor is this sensor tech SGX MIX 4514, may be useful to expand a little bit. As you can see, this is a MOS sensor with 2 fully independent sensing elements in one package. Now you can go into the details of this picture, but before we actually delve into it, what is important is, supposing you are interested in measuring the nitrogen dioxide concentration in the air, you have to get to use this chart. This chart essentially is giving you the nitrogen dioxide, right. The top one is telling you the cross sensitivity of such a sensor. It is cross sensitive to methane, propane, ammonia and so on and so forth, so many other related things. Of course, it is also measuring carbon monoxide, it is measuring CO, but when you are measuring CO, there are other gases also it is cross sensitive to. So, one of the problems with any of these air quality measurement units, particularly IoT applications and IoT sensors, is the cross sensitivity of the sensors. You have to really be very careful about, okay. That after all, we are electrical engineers, we will get a voltage. Whether that voltage corresponds to a particular gas that is present in the ambient, or whether it is corresponding to a mixture of gases, we do not know, because it is only a voltage. Therefore, you have to find a way to subtract the others, and then gas of interest you should pull out and so on. So, you have to do a lot of adjustments to actually pull out that particular thing, which is standard, I mean everybody does this. So, this chart is telling you that if you measure CO, you are not sure whether you are measuring H2S, ethanol, hydrogen, ammonia and so on and so forth. Your environment to a large extent will tell you whether that environment actually is also rich in other gases. So, you must know your environment. For example, if you are in an industrial setting, it is difficult to say what are the gases that are emanating, but if you are at home, you can be sure that you will not be playing with ammonia, for instance, right, or any one of them. So, you are actually could be measuring just the carbon monoxide present somewhere. Quite like that, the that is when you do a basically all these gas sensors, particularly the semiconductor gas sensors, do this oxidation and reduction process, right. So, this is the reduction process which gives you the carbon monoxide, and the oxidation process gives you the NO2 gas. But again, NO2 gas here is cross sensitive to NO as well as to hydrogen. Having discussed this cross sensitivity, supposing you are interested in finding out the ppm level of nitrogen dioxide, right. How do you do that? This is the only chart available with you. On the x axis, this is a log scale. On the x axis you see the concentration in ppm, and on the y axis you see a ratio of Rs divided by R naught. Okay. Now this sensor is supposed to give you Rs and Rs as well as R naught. Now R naught is something that you have to somehow make one measurement under a clean environment. You have to do it, assuming that there are no gases around you, you make a measurement of that R naught value. R naught is nothing but a resistance value. You have to get hold of a resistance value which this system is actually giving. Then RS essentially is the measured value of the NO2 that you are interested in making a measurement on. That is an environment where there is the gas of interest. R naught is the environment you have placed, maybe it is a testing chamber, maybe it is a calibration place, somewhere where you are calibrating the sensor and you are obtaining R naught. Then you take the ratio of R naught, RS by R naught, you will get a number. You can see that this number is along the y axis. Corresponding to that, if you read off the slope and you do a simple expression and you read off the, look at the slope, then you will actually essentially be able to read off the concentration value. So from this picture itself you will be able to read off the concentration value. Now let us shift to the way by which this code is implemented, and I will show you in software how exactly this code works. On the screen you can see that you are actually obtaining the resistance value which essentially is marked there. So that mark actually is reading the resistance value RS, right, and you can see that expression essentially is trying to read that. The circuit given by SGX sensor will actually tell you, the reference circuit will actually tell you that you have to put this expression in order to make a measurement of the RS value. Repeat the same process to get the R naught value as well, right, into a clean environment where you know that there are no gases around, and that gives you an R naught value. So together you come back with the R naught, RS by R naught into this into the other data sheet and then make a measurement. So you can see that the ppm value that you are actually measuring is based on simply that the other graph that I mentioned to you, right, the graph which I showed you. You just read off the ppm from the x axis when you know the RS by R naught, which you have actually found out in a painstaking way. You have done this R naught calculation and you have done the RS by R naught. So after that you print the ppm value, the gas sensor is ready now to show you all about the ppm values which are being read as the nitrogen dioxide values as it is being read. So you can see now that ADC value of something tells you output voltage is 1.27, sensor resistance is some value, and the concentration of nitrogen dioxide is so much ppm. So you can see continuously it is it's actually what we are showing you is live in this classroom. You see that ADC value is changing to some extent, and the corresponding output voltage as given by the sensor is shown there. The sensor resistance is calculated as we discussed. RS is actually being shown there. R naught is already known to you because it is a one time activity that you do an R naught. So RS is being displayed, then use RS by R naught and put that simple expression to calculate the ppm value. That is about what we have here in this demonstration. Thank you very much.